Now we're going to be covering Chapter 7, Determining Empirical Formulas. And our objective here is if I give you some experimental data that has how much percent you have of each compound, or each element in a compound, you'll be able to calculate a compound's empirical formula. Let's do a little bit of review here on some definitions. If we have a molecular formula, this gives the real number of elements in a compound, and specifically in a molecular compound. Remember, a molecular compound means it's going to be two or more nonmetals only combining. So some examples of molecular compounds would be nitrogen dioxide. That would be one. But another molecular compound is dinitrogen tetroxide. We have various carbon-hydrogen compounds like C2H4. That's an actual molecule. Now, molecular formulas, we don't reduce these because then it's no longer the same thing. So even if you had N2O4, you would not reduce it to NO2 because this molecule is different than this molecule here. Now let's take a look at what an empirical formula is. An empirical formula is the reduced formula. So it's a reduced formula. You're going to reduce the subscripts if you can. And you're going to get it to the lowest whole number ratio of atoms. So we can take a molecular formula and reduce it to an empirical formula. And let's do some examples so that you get the hang of it. We're going to have one column that labels molecular formulas. And then we're going to convert them to the empirical formulas. So let's say, for example, that we did have dinitrogen tetroxide. That is the molecular formula. Both of these can be reduced by, or divided by 2. So the empirical formula for N2O4 is NO2. Let's say we had C6H12. This is called hexane. You can actually buy it in a hardware store. We can divide both of these by 6. So our empirical or reduced formula would be CH2. Let's say we had C2H4 or H2O4. We could divide that by 2. We can divide that by 2. We can divide that by 2. So our empirical formula would be CHO2. Now let's say instead we have something called pentane C5H12. That is the molecular formula. If we look at this, we cannot divide these numbers by any common factor. So in this case, our molecular formula and our empirical formula are identical. Okay, what we're going to do next is determine the empirical ionic formulas from experimental data. So I'm going to pause here and create another page. Okay, let's figure out how to work one of these using an example. We have a detective. He finds an unidentified white powder next to a dead body. He takes the powder to the forensic lab, and the lab identifies it as containing 16.4% arsenic and 83.6% iodine. What is the empirical formula? So let's take a look at what we're going to do. The first thing we're going to do is we're going to convert percent to grams. And I want you to space it out on your paper just like I'm doing. So we're going to have 4 columns here, so save your space. So I'm going to have 16.4 grams of arsenic. And I want you to skip down about 4 lines, 1, 2, 3, 4. And I'm going to have 83.6 grams of iodine. That would be 16.4%, 83.6%. So in other words, we're pretending we have a 100-gram sample. The next thing that you're going to do, so that's step number 1, is you're going to, in step number 2, is you're going to convert grams to moles. So we started off with 16.4 grams of arsenic. We need to get to moles of arsenic. So the molar mass of arsenic is 74.92 grams of arsenic for every 1 mole of arsenic. And if we figure that out in moles, we get 0.219 moles of arsenic. We're going to do the same thing for iodine. So the molar mass of iodine is 126.90 grams of iodine for every 1 mole of iodine. And we convert that into moles, and we get 0.659 moles of iodine. Step number 3, convert moles to subscripts. So we're going to take these two, and we're going to make them into the subscripts. So we'll have arsenic, 0.219, and we'll have iodine, 0.659. Now, we know that we cannot have subscripts that look in this type of form, we have to have whole numbers as subscripts. So our last step is we're going to convert subscripts to whole numbers. So convert subscripts to whole numbers. And the way we do that is we divide these subscripts by whichever one of these is the smallest. So this would be divided by 0.219 and divided by 0.219. And when we do that, we get arsenic, and a number divided by itself is 1. And you plug this in, and you get iodine 3.01. Now, remember, this is experimental data. So there's going to be a little bit of what I'll call slop or error in it. 3.01 is pretty darn close to 3. So our empirical formula is arsenic, we got rid of the 1, iodine with a subscript of 3. This is a molecular compound because they're both from on top of the staircase, so this would be arsenic triiodide. So once the detective has this, the detective can start looking for somebody who might have gotten their hands on some arsenic triiodide in the past, a long, long time ago. This stuff actually used to be treat diabetes. So in the past, this was used to treat diabetes. So your detective has to find somebody that might have been able to get their hands on this, and then at least he or she has a start on solving the case. Okay, we're going to do one more problem. Here's our second problem. We have a compound that contains 25.9% nitrogen and 74.1% oxygen. So let's follow our steps. We're going to convert percent to grams. So we converted 25.9% nitrogen to grams of nitrogen, and then we converted grams to moles. So we divided through by the molar mass to get 1.85 moles of nitrogen. We did the same steps with oxygen, so 74.1% oxygen became 74.1 grams. We converted to moles to get 4.63 moles of oxygen. Now, we're ready to convert the moles to the subscripts, so we're going to take both of these, and we have N 1.85 O 4.63. We have to do the next step, which is converting the subscripts to whole numbers. So we divide both by 1.85. And when we do that, we get nitrogen 1 and O 2.50. Do not round this. If you take a look at this, we can multiply both of these by 2. And if we multiply both of them by 2, then we get a whole number ratio of N2O5. So sometimes you end up having to multiply by another whole number to get your subscripts to whole numbers. Let's try another one. Let's say that I have, after I go through my reducing, that I had N1O 1.33. Don't round this down to 1. See if there's something real easy that you could multiply both these numbers by that way you would still end up a whole number. So what can you multiply 1.33 by and get a whole number? Well, 0.33 is very close to a third. So if we multiply both of these by 3, our new empirical formula would be N3O4. So you should recognize certain decimals as being fractions. So for example, if you see an 0.25 or an ending of 0.25, you know that you can multiply by 4. If you see an ending of 0.66, if you multiply by 3 again, you're going to get once again to a whole number. Now let's say that you had 0.65. Remember, this is experimental problems. So the 6.5 is pretty darn close to 6.6. So go ahead and multiply by a 3 again on that one. And you'll end up getting to whole numbers. Now the fractions that you should be familiar with, because I won't go any further than this, would be quarters, or thirds, or fifths, or halves. I'm not going to do anything beyond that. Okay, that is the end of empirical formulas.